My name is Luke, and I'm going to be talking about three-factor learning rules for learning synaptic and axonal delays. So some background, three-factor learning rules, they have three factors. So the first two factors are a function, essentially they comprise the eligibility trace, and which is a function of the presynaptic activity and postsynaptic membrane potential. And essentially, it tracks the activity of the synapse across time. What differentiates these rules from Hebbian learning style rules is that the eligibility trace, the value of the eligibility trace is modulated into a synaptic change in the presence of the third factor or the learning signal. So the second aspect of this work are the delays. So spiking neural networks are able to process both time and space, but the parameters that they have that can contribute to temporal pattern recognition lie in the neuron parameters. So by adding delays that would allow us to essentially manipulate when the spikes influence the postsynaptic membrane potential, this can allow us to have an exclusive parameter set that allows us to perform temporal pattern recognition. So how do we do this? We start with the equation for the neural dynamics, the differential equation here at the top left. We solve it analytically and then discretize it. Then we use eligibility propagation as the basis for implementing the learning rules. So essentially, eligibility propagation reformulates the gradients, which is the derivative of the error with respect to the neural network parameters of interest as a three-factor learning rule. And it shows that under some constraints, these two are equivalent. So in our case, the fundamental problem to apply this to delays is that we need the derivative of the membrane potential with respect to the neural parameter of interest, which is, some of them is the delays. So we need to differentiate this equation with respect to the parameter of interest. So for the ways, this is easy, but for the delays, we need to differentiate the spike train. And since this often takes the form of a Dirac delta function, it is by definition non-differentiable. So the way we overcome this is to represent the spike as a continuous function, which we do by using a Gaussian, and then we can calculate the gradient, and therefore we can calculate the eligibility trace. So we apply these rules for synaptic and axonal delays and investigate their effects in feed-forward and recurrent networks. And we do this using the spiking Heidelberg digits dataset. So on the figure on the top, we show this for synaptic, for feed-forward network, sorry. And by adding the synaptic delays or the axonal delays, we see we can get a roughly 13% improvement in classification accuracy. But the problem is that we cannot distinguish if the delays are the learnability of the delays makes a difference versus adding them fixed and non-learnable. So we remove some of the redundancy of the neural network, either through sparsity or a reduced model size. And then we can see that the neural network, the learnability of the delays can contribute up to 6% in classification accuracy. So we also do this for recurrent networks. And essentially, the result is somewhat the same. However, since the recurrent networks are more versatile, their baseline over a weights-only implementation is smaller. And also, they exhibit a bit more robustness under sparse conditions. So to conclude, maybe the key takeaways of this work is that we have three-factor learning rules for both synaptic and axonal delays that would allow us to learn all of the network parameters online. So in case of applications that are running on resource-constrained hardware, having this parameter heterogeneity is very important because it allows us to have smaller models and at the same time, we get higher accuracy. So the classification accuracy per model parameter is very high. Thank you very much.